1.7, our goal is to solve absolute value equations and inequalities. If you don't remember what absolute value means, you'll see it very soon. Absolute value of x equals some number means how far is our distance between 0 and that number. Distance is always a positive number. So for example, if I were to say absolute value of x equals 5, that means we could choose two numbers for our solutions. There are two numbers that are 5 away from 0. There's 5 and there's negative 5. So there's two solutions. It gets a little trickier when you've got something on the inside. X minus some number in absolute value equals k. There's still two answers, but this time we go to whatever that b number is and then go k units in each direction. So we'll see that in the next example. And then we'll see an algebraic way to find the answers without having to draw a graph. So the absolute value of x minus 5 equals 7. Graph the solution. So what that really means we want to do is start at 5 and go 7 in each direction. That way we get 12. The other direction, if we go that many units, 7 units, we get to negative 2. So there's our two solutions, negative 2 and 12. There's an algebraic way to get the same answer, and it's actually a little bit easier and more useful in the long run. The way we would handle this is we say x minus 5 could equal 7, or x minus 5 could equal negative 7. So we could really go 7 forward or 7 back and get our two answers. That'll give us the x equals 12 and the x equals negative 2. And we always separate our answers with an or on these types of problems. That's really the key to today's whole lesson, is how to do something like that. This box tells us how to do it the way I just showed you. When you've got an absolute value of something equals something else, you just split it into two equations, one with the positive c, one with a negative c. Then you go back and solve. Step 3 says check your solution. You should always check your solution. I'll tell you when it's going to become most relevant. You can kind of tell which ones are going to have bad answers by looking at them. The way you're going to see bad answers is if this would have said 45x, that's a red flag that you're going to have an extra solution that doesn't actually work. We'll see that in, I think, the next example. But we'll check our answers on this one also. Solve an absolute value equation. We write 5x minus 10 equals 45, or 5x minus 10 equals negative 45. We then go through and solve both of these. To get our two answers, to check these answers, we plug them into the original. So first we'll check the 11. Plug it into the original equation. 5 times 11 is 55, minus 10 is 45. Looks like it worked. Check the negative 7. 5 times negative 7 is negative 35. Minus 10 is negative 45. Absolute value of negative 45 is 45, so it worked out. This time it tells us to check for extraneous solutions. Turns out there is one. The big red flag is the x on the outside of the absolute value. We start off exactly the same as the last problem, then we'll get our two answers. Once you get your two answers, a keen eye is going to actually let you see which one's bad in the first place. I can see that the negative 2 is going to be bad because 4 times negative 2 is negative 8, and absolute value of something can never equal negative 8. But we'll check both answers for extraneous solutions. First, I'll try the 6. 2 times 6 is 12, plus 12 is 24. Plug 6 into the other side. 4 times 6 is 24. So 6 was okay. Plug in the negative 2. 2 times negative 2 is negative 4, plus 12 is positive 8. 4 times negative 2 is negative 8. Absolute value never equals a negative, so that's bad. That's extraneous, so the only real answer is x equals 6. That's the end of that one. At this point, you can pause the video and try these on your own, or you can do those later. Kind of a little cheat sheet here. Tells you what your graph's going to look like on inequalities. If you see a less than, tells you to use two open dots and shade in between. Less than or equal to is the same thing, except you use closed dots. Greater than, we shade outwards like an or. Greater than or equal to, we also shade outwards like an or, but we fill in the dots. The reason for that is when you see something like this, it means to do the and shade in between type. When you see a greater than, it means we're doing the or type problems. So we're going to see that in the next example. It says 4x plus 5 absolute value is greater than 13. See greater than, that tells you right now that you need to split this into an or type problem. And then we graph. One thing to note that you can also see on that chart on the previous page, I changed the sign on my second inequality just like I always do, but I also flipped the sign. You do that every time, whether it's the ands or the ors. We need one greater than, one less than. Other than that, we solve like normal. For your final product, I'm kind of looking at a lot of things here. I'm looking for the x's greater than 2. I'm looking for the word or. I'm looking for x's less than negative 4.5. And I'm looking for your graph. And on that graph, as always, I'm looking for your open dots and your direction of shading. It's all got to be there. At this point, you can pause the video and try these on your own, or you can do these later. Word problem. A professional baseball should weigh 5.125 ounces with a tolerance of 0.125 ounce. Tolerance means it could weigh a little bit more, could weigh a little bit less, and that tolerance number tells you how much more or how much less. If you're outside those tolerance levels, it's not qualified as a professional baseball. So the way we're going to say that is we want our baseball to be somewhere close to 5.125. And when we subtract the actual weight of the baseball from 5.125, we shouldn't have a number any bigger than 0.125. Notice because of the absolute value symbol, we're allowed to be a little bigger than 5.125 or a little less, but not too big or too small. So now we're going to solve this inequality the same way we would any other inequality. Notice this time it's a less than, so we're using an and. That means we're going to put our negative 0.125 less than or equal to the inside, less than or equal to 0.125. Once we solve this inequality, we're done. After we're finished with that, we see that a professional baseball can weigh anywhere from 5 ounces to 5.25 ounces. Otherwise, it's not legal. And you can measure the weight of your baseball at home. If you have one, it should be right in there if it claims to be a professional baseball. Our last example is kind of the same as the one we just did, but looking at a different way. It says the thickness of the mats, the rings, used in the rings, parallel bars, and vault events must be between 7.5 inches and 8.25 inches. So we know the thickness needs to be between a certain two numbers. Notice that's kind of like we started with the final answer from the previous problem. We need to figure out what number to put inside our absolute value. And just like the previous problem, that should be whatever the average weight is. Last time it was 5.125. To find our average weight here, we're going to add up our smallest weight and our biggest weight to figure out what number we want to put in there. Adding up and dividing by 2, we see that the average thickness is going to be 7.875 inches. Now we need to figure out our tolerance. That means how much bigger than that can we be? And that's a simple subtraction problem. We'll just take our maximum thickness, subtract it from our average thickness, and that tells us the tolerance for the thickness of the mats. It turns out to be 0.375. And we're done. What this really says is if we measure the thickness of the mat and subtract it from 7.875, and then take the absolute value of that number, we'd better get a number smaller than 0.375 inches. If not, we don't have the correct thickness of a mats for the event. At this point, you can pause the video and try these on your own, or you can try these later.